field of thermoelectricity. It's a field which was started by Seebeck in the year 1840, but even today it is very relevant because we are now finding newer materials in which these effects are greatly enhanced. So I will give you a feel for why this field is still interesting, and we use it extensively. I think everybody uses a thermocouple. But then, my lecture is based on why a thermo-EMF should arise in terms of our modern picture of a metal, in terms of the electronic structure. We need an explanation. It is to measure something like what an engineer would like is just to make a measurement and use that one for his property. But as physicists, we ask a question, why an EMF should arise at all? What is the basis for that? So I hope to give you a feel for that. And two experiments are set up. In one particular thing, this is called as thermo-EMF analyzer. This is an equipment in which you can study the thermo-EMF of any pair of metals right from, say, from room temperature up to about 800 degrees Celsius. It's a small furnace. I will show you all those things in the laboratory. We can go and a simple arrangement. And we also prove to you through experimental means that through this experiment we understand what is meant by the absolute Seebeck coefficient of a material. It's an absolute property, like resistivity. Normally we always associate thermo-EMF. Now I will analyze it in terms of the property of an individual metal or another one. What is it related to? I think my discussion now and in the afternoon, my first lecture will be about understanding the physics of thermocouples. Best way to do this is to go through historically how this effect was discovered and what are the newer developments and who is the first person who really understood this phenomenon. Very well, even before the modern quantum theory of metals came in, through great physical illusion, one person understood it very effectively. Of course, he is our famous Kelvin. He was known as Thomson earlier, who became Lord Kelvin. And you have all heard of Kelvin in various your temperature scale, great man in thermodynamics. How one particular experiment which you are going to do is the experiment which made Kelvin discover an effect called the phase. So we will go through that in some little analysis. My entire, all this transparency, everything, there is a model, TGR, IISER Mohali, you can all download it and use it anywhere you like it. So, I will deal with the physics of three effects called the Seebeck, Peltier, Thomson. All the three are related, but I will show you how they are. Then, I will briefly describe you to the experimental setup of how to study. And a particular example I have chosen here is iron copper. It's a very nice experiment, historically important experiment, and I think it used to be there in the syllabus of the B.Sc. Is it still there? Still there? Fine. You please see. Some of them, but you require to do studies up to about 400, 350 and 400 degrees. So many of them don't have a furnace to go to for. That is the problem. But now I tell you, it is not so difficult to build this one. Well, once you do the experiment, I want you to carry it to your laboratory and do this experiment. I think that is the purpose. I also like this. I did this experiment not in my college days. I did it only in my laboratories for the help of college teachers. And then I will deal with the physics of what are called as neutral and inversion temperatures. We teach neutral temperature, inversion temperature. What is that concept? How it arises through this experiment. Another related experiment to this is to verify what is called as the law of intermediate metals. That is very profound experiment, very important theoretically. We have set up in the same experiment, we do two experiments in one shot. One is to study the neutral temperature, inverted temperature, and then other is to verify the law of intermediate metals. Law of intermediate metals, according to me, is so fundamental, and it tells you that it is a very intrinsic property. How it is? Those who are engineers, we call all this thermocouple, everything is a transducer. Transducers are generally the systems wherein is a sensor which converts the physical property of interest to an electrical quantity. We call them as electrical transducers. You can have transducers like measuring your wall used to one type which is very common is the platinum resistance thermometer, correct? Or TDs as they call it. What we use there, the property, the resistance of platinum behaves linearly with temperature. Therefore, if I measure resistance, then it is equivalent to measuring temperature because I know the slope, I have got this thing here. So that is one property. That is, but to measure resistance, importantly, you must pass a current. You require an external source, power source, then to measure the resistance. But there is thermocouple in distinction to it. Again, it measures temperature, but you don't need any other factor. It generates the EMF by itself. Therefore, we call this as an active transducer. An active transducer. Resistance thermometer is a passive transducer. You require an external energy. But thermocouple is an active transducer. You just take a pair of metals, take a junction, and then keep it at a temperature different from the surroundings, you will get a voltage. Correct? That is it. So that is the intrinsic, and we are asking the question, how physically a voltage should arise? What are it related to? These are the fundamental. I have listed all these things for different transducers. You can go through it, RTD and this one. Another is called strain gauge. If you want to measure small changes of length, strain is change of length per unit length. Therefore, strain is measured by again using a property in which the resistance of a material is linearly related to length, correct? Or equal to rho L by A. Resistance. Rho is for the resistivity of the material. Length is the length of the sample. Area of cross section is T. So, if length changes, resistance changes. That property is used to measure in a strain gauge. That's all. You make a strain gauge, you essentially measure resistance, and you can relate it to what a gauge factor, the corresponding strains. You can measure micro strains, strains of the order of 10 to the power -6, very easily by a technique like this. Like that, several things are there. Thermistors also you would have heard. Thermistors are nothing but a semiconductor in which resistance changes very markedly with temperature. You can measure small changes of temperature by a thermistor. And there is something very much more fundamental. This is called an IC temperature sensor. If you have got a matched pair of transistors, could be NPN or PNP, matched pair, and then if you pass a well-defined current in the collector current, then the base emitter voltage, the difference in the base emitter voltage, when the collector currents are a constant ratio, then this difference in the base emitter voltage is directly proportional to temperature. This comes from the fundamental relation between voltage and the currents. It is a matter. Basically, you can do that now. I can show it to you a little later, but it is so fundamental. The difference in the base emitter voltage is directly proportional to temperature. So, I measure the voltage, I measure the temperature. Why it is important is, for the modern way, I have got my computer here. It has got a central processing unit, our CPU. The CPU will break down if the temperature of the crosses a given point. Therefore, we integrate that CPU unit with an integrated IC temperature sensor. because it is done out of semiconductor thing only. The same CPU. That one, this is integrated and it measures the temperature constantly of my device. In fact, many of you who are used to computer hardware, they know that if there is a thermal cutoff, if the temperature were to cross beyond that one, it power to the computer, that part gets based on this sensor or the integrated circuit. It is used, a very important thing. But as physicists, we can understand that one in a very simple way. I will show you the equation. Now, I come to historically. Let's pay our great respects to this man by name Thomas A. Seebeck. He was in the year something like 1821. Same period of time wherein Michael Faraday hoisted the important discoveries in electromagnetism were all done. We were understanding how by passing a current it can produce a magnetic field, right? Or how by changing a magnetic field we can produce a current. All these laws of induction, famous things for which modern life is built around from that time to now. He lived at the same time, 1851, but he was a biologist. Then ask a question, why biologists was interested in this? At that time, they were all natural scientists. That means anything which appeals to them, they will experiment. Experimentation was something important to experiment to try something. So they were all, we call them instead of scientists, many of them we call them as natural philosophers. Raleigh, for example, who first showed us why the view of the sky is due to, he was a natural philosopher. That means he looked around you and tried to understand nature as a whole. And I think Raleigh was like that. So in that genre, there were several scientists in different fields. He was a biologist mainly interested in frogs. He had done extensive work on frogs. But he somehow did an experiment wherein he connected a pair of metals like A and B, kept at one junction at a different temperature compared to the ambient temperature. T1 is say ambient, and then he connected a voltmeter. So if this temperature is different from this, we showed a voltage. Mind you, the circuit is not complete, it is an open circuit. It gives you a voltage. But suppose you make a closed circuit, a current will flow. As long as the temperature here is different from the temperature here, right? So a closed circuit and an open circuit. But we are mainly interested in the open circuit voltage. That is what is here. So the voltage is directly related to this temperature difference between T2 to T1. It's not strictly linear, but larger the value, larger is this voltage. That was the experiment. He did tremendous amount of work on different pairs of metals. In fact, probably you will normally teach, there is something called as the Seebeck series, right? He classified experimentally. He did so much of experiment. He put in several numbers depending on the values which you got for the various voltage. So he made the Seebeck series. And it includes today of materials what we now call as semi-metals and semiconductors. It was not known in 1820. We didn't know why something should be metallic, why something should be a semiconductor, why something should be an insulator, or why something should be a semi-metal. We didn't know. Theoretically, we had not understood. But experimentally he classified it, and today its value is there. Although he made this important experimental discovery, he did not understand the importance of this. He did not. He did not, for example, think that it is electrically knowledgeable. Like, if you take a circuit like this, a closed circuit of two different metals, there is a current, and therefore, because it produces current, there is a magnetic field associated. Suppose you put a magnetic field outside that gets deflected. That is how Faraday, Oersted, etc. understood this phenomenon from their effect, because it depends on how you produce the current. Here current is produced by thermal means. It doesn't care magnetic field is produced because there is a current. It doesn't matter whether its current is produced by having a battery or whether current is produced due to a thermal means. It just doesn't matter. That's all that. But he didn't understand it this way. So, but nevertheless, his experimental contribution is very, very fundamental. Whatever he experimented, series and everything what he did, very fundamental. Now, I have explained the same thing. Now we relate. Now it comes to the density matter. And also a lot of misconceptions when we teach thermoelectricity. Somehow, most of the books I saw, especially at B.Sc level, it is put as the effect is that generated at the junction. They think it is something to do with the nature of the junction, and it is voltage is produced in junction, which is a misnomer. It is not produced at the junction. It is produced all along the length of the material. Only thing is, it gets manifested because of the junction. We relate it. Now we relate it, and my next discussion, probably about 20 minutes or 25 minutes, is to convince you about what is called as this absoluteness of this effect. That means, instead of thinking two different methods, now we argue out, because now we understand. I think we teach matter physics at some level to college students. I think B.Sc, we teach matter physics, it's something connected, that is the quantum theory of matter. So, I will now give you a little introduction to that, and then now we discuss in terms of a given matter. Simple. What we understand, the simplest method to teach is sodium. It's an alkali metal. What is its electronic configuration? 1s2, 2s2, 2p6, 3s1. All the shells below 3s, they are all full. The atomic shells are full. And now, how do I make a metal? As a theoretician, I can make a metal by bringing sodium atoms from infinity to the distance which is your interatomic spacing in the lattice. Right? Now, you have to argue out what happens to the individual electronic levels that once you bring from infinity to the characteristic distance. For that to understand is, after all, a solid is a giant molecule. Go through the simplest diagram. Make two atoms put together. Hydrogen molecule. Hydrogen is a molecule. This is famous Hydrogen steel, which it is called. What do you do? I got 1s level of one hydrogen, another 1s level. You bring them together. Then this you form what is called as the molecular orbital, which is a linear combination of these atomic particles. Then you get two types of states. One is called the bonding state, another is the bonding state has got an energy lower than the energies that they are infinitely apart. Right? So what is these two forms like this two levels, right? So a molecule is formed because you get energetically less, right? You're lowering the energy. And similar way, now when you bring n atoms from infinity to together, then each level which was a singlet level now will form a range of energy. So we form a band of states. And now the next question you have to ask is to explain to them is, how do I fill those states with electrons? Then you have to importantly bring in Paul's exclusion. Because the electrons are Fermi particles, they have got a spin half. You can put maximum 2 electrons into a given state, and those two things have to be opposite. Then once you have got this individual state, correct? That's how You can't put every of those things into the ground state, it goes into filling. If the individual atomic shell is full, like the 1s2, I have got 2 electrons, right? And now that band which is formed, you have got n number I put it, I have got n states, right? But each one can accommodate 2, therefore that will be full, right? Each one, because it has got 1s2. That's how all these lower states are full. They don't conduct electricity because if it has to conduct electricity, it must go to the next state. They are completely not allowed because that's a gap. Therefore, it does not. This happens up to 3s. In 3s, what happens? I have got n number of states. Total number it can hold is 2n. Because each one can hold 2. But I have got only n electrons. Each one is contributing only 1. Therefore, that band is full and it conducts. Fine? But in order to describe this in mathematical terms, what we do, we have got our Fermi distribution law for the group of electrons which are now my metal. So my metallic state is now a group of electrons which follow the Fermi-Dirac statistics. That statistics we all know the Fermi function. This is Vm cost. They are full up to the Fermi energy. Important thing you realize the statistics which has played an important role. Even at t equal to 0, even at t equal to 0, classically, all the electrons would be at rest. But because of this degeneracy, whatever is the Fermi-Dirac statistic, electrons are moving. Ef is of the order of few electron volts. Can you calculate the velocity? What is the order like? Anybody?
10 +
Yes.
7.
Right. So electrons, even at t equal to 0, are moving with a velocity something like 10 to the power 7, 10 to the power 8 centimeters. Enormously mobile, even at t equal to 0. Right? So distinct from the normal velocity. And what is at a given temperature? This is again very important. This value is half. The Fermi energy at any temperature, finite temperature, is defined at the depth level, which corresponds to the probability of occupation, which is half. It is between 0 to 1, and therefore this value is half. What this means? Yet electrons which are here get shifted to the states above. There are empty states above. And this explains another very important things when we teach physics. Normally, if you take specific heat, we teach what is called as Dulong-Petit spin. Right? That is, it comes from the central theorem in which you associate with each degree of freedom a characteristic energy, half kT per degree of freedom. Fine, we argued out half kT per degree of freedom. Now I have got the electrons, which are n electrons. Each one is 0, n electrons. So what should be the specific heat associated with it? We can calculate theoretically, very simply. It has got 3 directions, x, y, z. Each direction, it is half kT. So the average energy of an electron classically is 3 by 2 kT. And therefore, its specific heat is its derivative with respect to temperature. It is 3 by 2 K. Or if I have got n, it is 3 by 2 n K or 3 by 2 R. It is all gas constant 3 by 2 R. So, this gave rise to a big problem for classical physics. If you take the case of an insulator and a metal, you would expect theoretically, classically, the specific heat of a metal should be much higher than that of an insulator. Correct? Because you have got free electrons here. They have got greater degrees of freedom, which should be different from the normal insulating. In the insulating thing, what is it? They are all atoms of the molecule which which are bound together, and there are 2 degrees of freedom there. One is potential energy, another is kinetic energy. Half kT per, it is called equipartition degrees of freedom. Classically, thermodynamics goes to do. It is half kT per kinetic energy and half kT per the potential. So it is kT. So you can do for the Coulomb-Fetish law, which is like kT per each mode of operation. So that is for the insulator. For the metal now it is. So metal it is 3R plus 3 by 2R. It is so different for a metal compared to insulator. But you go to internet, check the values of the specific heat of a metal and an insulator. They are not too different. They are of the same order. It is not so different like what it would tell us. What has happened? Why the electrons in a metal does not have the classical value of this. This was a fundamental question, and this is you are taught. What is it due to done from this curve? This curve, if you look at it, it is the tail of the Boltzmann's distribution function. Same tail. What it means physically, I tell you, is so simple, and you can do an order of magnitude calculation straight away, and you will get the right order of magnitude, which is the theory of the electronic specific heat. It is very important even for my discussion. That's why I am doing it for you. You see here, if I heat a metallic system, only electrons round about the Fermi energy can absorb the energy and go to the next state. Those electrons which are deep inside the Fermi sea, they cannot, because what is the order of kT? What is the order of magnitude? Again, in physics, orders of magnitude are very important. What is the order of kT?
25 electrons.
Correct. Yes, 25 millielectrons. So we always use the right thing. That is the electron volts. This is millielectrons. Very small, isn't it? Therefore, the next stage, these things are all full. It won't take part. You go only close to this Fermi energy, electrons can shift because the next states are empty. Right? Therefore, they can take part. So, effectively, the statistics, what it effectively means physically, out of so many number of electrons, only the fraction of electrons, which is of the order of kT by m. That means the electrons in the shell of kT, close to Fermi energy, they are the only ones which can take part in the thermal process like a classical. You can apply the classical equipartition thing to this fraction kT by m. So, what is the energy like? 3 by 2 kT into kT by m. But please remember, what is kT by m? It's such a small quantity, right? You can do this. So now, this is the total energy which is associated, and therefore the specific heat, the electronic heat, will be equal to, this is T square, so square feet, it becomes a linear term, T, right? And then kT, K square, that is 3 by 2, K square, T divided by this is what ion. This is something very fundamental. This is called electronic ion. The electronic specificity is directly proportional to temperature.
This is again the classical thing you have done.
This is finally with Fermi-Dirac statistics with the classical thing. But you can do the entire quantum mechanical bit.
We should calculate the density of states.
Yes, yes. Density of states, where it is included. 1 by EF is nothing but the density of states. Equal.
I am telling you that number of electrons that you
Yes,
calculated
correct.
by EF.
Yes.
That is not a proper thing to write.
This is done for the completely free electron thing. Completely free electron thing. It gives the essentially the physics of the same thing for everything. You can do 1 by EF is nothing but density of state. Electron specificity is high if the density of states is high. Right? Let's take it. So the same formula is there. What I wanted to tell you physically is to when we teach students, that is how you go from one statistics to another statistics. What is the physics which is that part of it comes out very clearly. It's an order of magnitude. You can do completely from taking A, N, E, F, E, D. Take the total number. That part. So this electronic stability, because EF is very large, is an extremely small quantity. It is 10 to the power minus 4 of your classical value which you expect out of that of the electronic system. Therefore, this is something very fundamental. So please remember from my discussion why I am bringing you in the background of how to understand thermoelectricity. I am preparing you for the background. Sorry. So having told this, now the EMF which is now related to T2 minus T1, the temperature difference, and the product which is there, that proportionality, is the difference in the properties. Now I define is in the difference in the properties of metal A and metal B. Sb minus Sg. It's in the difference is there. Now we argued out. Because it is the difference, what should happen if I have same metal instead of A, B, have A, have another leg also A, connect to a voltmeter. Whatever you do for that one, if you connect a voltmeter, you will get a null value. That is the experiment. But it is null value. How we understand that null value is part of the discussion, which I do now. Okay. Now, please see here. I have now brought down theoretically the discussion into a single metal, wherein I create a temperature difference, argue out what happens. That's all the essence of thermoelectricity. I now take only one metal. Final for measurement you require two metals. But for discussion, for understanding theory, you require a single metal. Now, I take a single metal. I create a temperature difference between this end to this end. Argue out according to Fermi-Dirac's thing. What happens? Right? Please remember, if you do this Fermi energy at any temperature T, this is Fermi energy at T equal to 0. This is a very fundamental equation. This is something which we prove. The Fermi energy is not constant with respect to temperature. The Fermi energy shifts slightly down with respect to energy as you go to higher temperatures. Because physically what it means is, if the density of states were increasing with energy, as you go to higher and higher temperatures, electrons get distributed to the higher ones. In order that the total number of electrons is same, the Fermi energy, which is the probability of occupation of half, gets shifted backwards. So the Fermi energy is a function of temperature. Right? Please remember that. But it is a small correction. It is the second T square term. There is no linear term. T square. It's a small. Now, what happens? If I have got here a metal where this is at a higher temperature, this is at a earlier, if the temperature was uniform, Fermi energy was a constant throughout. Right? Fermi energy was a constant. So if you take any cross section, as many number of electrons will move from left to right as from this way. There is no current flow and its temperature is uniform, no ideas. Now, we come to a state wherein I have a temperature gradient. Now let us Fermi energy at one end is different from that at the other end. Fermi energy is like a chemical potential. Electrons move if there is a gradient in the potential. Correct? Electrons always move. Then once there is a gradient of the potential. This gradient you can put externally, like what you put in a battery, and make the electrons flow. That's how current comes. Now, internally, now I have created a temperature gradient and make electrons, because the Fermi energy is different between one region to another region for electrons move, correct? To equalize that time. When once the electrons move from the higher thing, this is called thermal diffusion of electrons from the higher temperature to the lower temperature. What happens? The electrons tend to accumulate towards the colder part, right? Your density initially before the steady state is reached tends to be an accumulation of charges. Because these charges repel, right? It produces an effective field. Internal currents flow in such a way that finally an electric field is established in the medium, in which there is no net current. The initial current due to this difference in the Fermi energy is balanced by an electric field which is produced in the body of the matter. Right?
Just like
Clear?
just like PM junction.
Just like, yes, exactly. But here I am not having any junction. It is given in a thing due to just a temperature gradient internally. And I take a metal bar, and in a metal bar it is an open circuit. I cannot finally have a current, but it does not exclude the creation of an electric field. So this is the essence of thermoelectricity. If I create a temperature gradient, I create an electric field, which is called the Seebeck electric field. That the electric field per unit temperature gradient is what we call as the Seebeck. So the electric field which I have put here, please see this equation. The electric field which is set in the body of the material is proportional to grad T. Electric field is a vector, grad T is a vector, right? S is a scalar. That S is what the Seebeck coefficient. So the Seebeck coefficient fundamentally is related to this electric field per unit temperature gradient. That's the fact in mathematics. It is the electric field per unit temperature gradient. If you are the voltage per unit temperature gradient, or E is S grad T, dt by dx. E dx, if you take, that is nothing but your voltage, delta V. So delta V will be equal to S into delta T. So that is a scalar equation. I can convert this vector equation into a scalar equation in terms of voltage and then temperature difference. Temperature difference is a scalar. T1 minus T. Right? So that voltage difference per delta V by delta T, that one is called as the Seebeck coefficient of a given material. And this magnitude of this electric field is dependent on the density of state, the Fermi energy, the scattering process of the electron. So it is very internally related to the electronic structure. So the electric field which is set up is now a property microscopically of the electronic structure of the given material. The magnitude of it, correct, is related. And now you can argue very simply. If I have got a circuit like this, this is A, same material A, T1, T2, T1. I connect a voltmeter here. It always shows 0 value. T1 to T2. Now in terms of that argument, now that is argued out fundamentally. It creates, then once there is a temperature gradient, we argued out there is an electric field. So let this electric field be EA, going from this temperature to this temperature. What is this other leg? It is again T1 to T2. This field is again EA in this direction. What is EMF? Fundamental definition. It is the work done by carrying a unit charge around this circuit. Right? I use that fundamental thing. This argued out. Here, now taking a unit charge from here, it is in the direction of the field. In this part of the circuit, it is in the opposite direction. The magnitudes are same. Whatever is work done in going from T1 to T2 is expended by going from T2 to T1. Exactly balances. So, physics argument is, it is zero nodal. It is zero because the two legs perfectly balance. There is a voltage generated in each leg, but it gets perfectly balanced. So, it is a null result. Null result is, one way is nothing is generated through, or two voltages are generated which are exactly equal and opposite. That is the physics way. That is the origin of the problem. Like why we always require a different method to have it. I think is that way the problem. But then, now we have got another nice way. Is there a material in which I create a temperature difference, but I don't generate any electric field? Is there a material? Huh? Is there a material? No, it is very small. It is not out. I know. It is neutral. Small value, but is there a material? There is a fantastic phenomenon which occurs in metals at very low temperatures. That it is superconducting phase. Okay, now it is so beautiful. Physics of it is very simple. What is a superconductor? In a superconductor, macroscopically, it can conduct current without establishing an electric field. Right? J equal to sigma E. Correct? Current density is directly proportional to electric field, and sigma is the conductivity. J equal to sigma E. Or the electric field is equal to J by sigma. Sigma is infinitely large. Right? For a superconductor, we call it is infinitely conductive. Therefore, the electric field is zero. The body of that. In fact, there are two characteristics of a superconductor. One is it is an infinitely conducting medium. Another, more importantly, it is a perfect diameter. Correct? These two things are very important. In fact, there is a beautiful description of the classical way of looking some of these things. In Feynman, if you read the third volume, it's so beautifully done. I always like it. What it implies is this: if Maxwell, he did the equations, Maxwell's equation, he did it in a normal state of metals, in which you see an asymmetry between magnetic fields and electric. Right? Here is a superconducting device. A constant magnetic field is associated with a current. You can produce a current even though you normally require changing magnetic field to produce a current in the graph. Here, what is it? Entire micro effect, whatever is that is connected with this perfect diamond is because current is produced. That part is something very, very fundamental connected with the symmetry between these equations, because perfectly symmetric when once you go to the super. Spectroscopic theories, they do theory like that. Please go through that, because for me still the greatest books of physics written from a fundamental point of view, making a student understand the beauty of physics. Nobody can beat Feynman. Feynman was one of the greatest teachers, probably in physics. He was a great scientist. He would not have been recognized very deep. His work is in quantum electrodynamics, like morning I was telling, the structure of the electron, infinities, renormalized group theory, sort of things like that. Not only he did got Nobel Prize for that, but I think he is recognized world over because he was a very fine teacher. And I think when you go to the board, he used to explain physics in his way. There are physics. So I believe when he had hundreds of students at Caltech, where he taught California technology, when he had a big classroom like that, the front row was occupied by 3 Nobel laureates. See, Nobel laureates are also of different classes in the Nobel laureates. Some are very good in their individual work, but not complete as physics. Feynman was that way, very unique. I always liked Feynman. In fact, if at all I like physics, to some extent even from my student day, it is because of my own personal interest in reading Feynman. I always strongly recommend to anyone. It is not like doing a derivation or something. It is just like to give you an essential physics connected. Only if you understand the essential physics, you can now do the mathematics. You have to understand that simple thing connected with which part of the electrons are really interacting in electron specifically, then you do the mathematics. You can do it rigorously connected with it, but you must get a physical content. And the physical content is only the electrons near the skin of the Fermi surface. I call it the skin of the Fermi surface. They can participate. So, having come to that, this part of the complete symmetry. Superconductors now, even though I create a temperature difference, electric field is 0. What it means is S, which is the Seebeck coefficient of a superconducting state, is ideally 0. It's my reference. It's a superconductor is a perfect state in which even if I create a temperature gradient, it does not produce an electric field. I use that as an ideal reference. So I will make a junction of a superconductor with my material A. I measure the voltage. What I measure is eventually that of my material A only, because the other one is 0. That's how we can now calibrate. Earlier, like what you suggested, yes, lead was chosen because it has a very small value of the, and that was the time for earlier studies. Now they have got a much better standard. Theoretically, it is 0. Therefore, instead of lead, we use this. Like whatever, lead also is practically good for most of our normal work. But superconductor is ideal. And this field got advanced very much more after high-TC superconductors. Yttrium, barium, copper oxide. I mean, it becomes superconductor not at liquid helium, but at liquid nitrogen temperatures, which we can do. In fact, at Bangalore, in our material science course, they set up an experiment in a closed cycle plant in which yttrium, barium, copper oxide is taken and you measure resistance as a function of temperature. About 80-90 Kelvin, the transition is so fast and so clear, beautifully comes to 0, and then the resistance becomes ideally 0. Beautiful transition. But the data, and if you later show it, I will put it on. You can see if you can't do that experiment here. It is done by all teachers who teach material science, or even in doing it's actually a physics experiment it can be done. But why it is important to material science is how to prepare yttrium, barium, copper oxide. That's the power of that. And why it is chosen. So that experiment. So that is with respect to that, the entire field of thermoelectricity.
How to determine direction of thermoelectric current? How to determine direction of your thermoelectric current? How to find direction of thermoelectric current?
Direction.
Yes.
Whether it's positive or negative. Yes, it depends. In this metals, in the metals, the Seebeck coefficient can be either positive or negative. Why it is so? I can only tell you in words, it's quite deeply involved. The electrons, the mobility, how it changes with temperature or energy. Maybe I should stop. I stop, we will come back. Then we will continue this because I don't want to get into your lunch time. And also I think hearing continuously for about 3 hours. quite strenuous for anybody. And if you don't know normally, you are